Hello everyone. Today we will talk about commonly used distribution for continuous and random variable. So the topics of this chapter are first Bernoulli distribution, binomial distribution, and Poisson distribution, and other distribution like the geometric distribution. All these distribution explain discrete random variable. Then we will continue with the continuous random variable and the famous normal distribution, log normal distribution, exponential, and other continuous distribution like the gamma distribution. Then we're going to learn how to use this distribution to do a point estimation of a variable. And then we will learn the probability plot technique to figure out what is the distribution, what's the density function or the mass function of a random variable. Finally, we will talk about the central limit theorem, which is a very powerful theorem. And basically, if you have a random variable and you don't know the distribution, or the distribution follow certain function like exponential, but it's not normal distribution. If I take a sample of this random variable and I find the mean of the items in the sample, then the mean of this sample will have a normal distribution. So we will talk more about the central limit theorem. Let's start with the Bernoulli distribution. We use the Bernoulli distribution when we have an experiment which can result in one of two outcomes. For example, flipping the coin. It's either head or tail. So if there is an experiment, we repeat the experiment and we get just two possible outcomes, success or failure. For example, sending binaries, zeros and one. It's either received correct or failure. Or you make a product and you are testing, are they working or not working? Then we call this a Bernoulli trial, and it will have a Bernoulli distribution. Now we can assign the probability of success P. That could be 0.8, 0.6, 0.4. Then the probability of failure will be 1 minus P. And that's what is the Bernoulli trial. Let's take an example. The simplest Bernoulli trial that we are familiar with is flipping the coin. There is two possible outcomes, either head or tail. And we can label head as success, tail as failure. And P will be the probability of head. In this case, it's always half. Probability of tail, it will be 0.5. If we make transistors and we test them, it's either working or not working. That's a Bernoulli trial. And probability of defective item may be 0.1, 10%. Probability of working item or success, 90%. So after we define a random variable x to have a Bernoulli distribution, then we will say the random variable x has a Bernoulli distribution, and the only parameter you need is the p, which is the probability of success. Now let's find the mean and the variance of the random variable x that has a Bernoulli distribution. First, let's show the probability mass function. So the random variable x has two possible values. One could be for success, 0 for failure. The probability of 1 is p. The probability of 0 is 1 minus p. So now if I want to find the mean of the random variable x, we use this equation. The mean is x times the probability of x for all possible value of x. In this case, x has two possible values, 1, and the probability of 1 is p, plus 0, and the probability of 0 is 1 minus p. So this is just p. So the mean of a random variable with Bernoulli distribution is p. Now if I want to find the variance of x equal x minus, this is the definition, mu x squared times the probability of x. In this case, I have x can be 1 minus mu, we found it just to be p squared. The probability x equal 1 is p, plus the second possible value for x is 0 minus the mean is p squared times the probability of x equals 0 is 1 minus p. So that's 1 minus p. So if we multiply all these, we get 1 minus 2p plus p squared times p plus p squared times 1 minus p. So this is p minus 2p squared plus p cubed plus p squared minus p cubed. So these cancel these, and we have p minus p squared, and this is p 1 minus p. And this is the variance of a random variable x that has Bernoulli distribution. Okay, let's look at this example. 10% of components manufactured by a certain process are defective. So P equal 0.1. X defective. A component chosen at random, let x equal 1 if the component is defective and x equals 0 otherwise. So 1 is for defective. What is the distribution of x? X, probability of x. So x could be 1 defective and the probability is 0.1. X could be 0, no defect, and the probability would be 1 minus 0.1, which is 0.9. So this is the distribution. Find the mean and the variance. Well, mu x is just p, so that's 0.1. So the average of defect is 10%. Find the variance of x, that is p times 1 minus p, so that is 0.1 times 0.9, so that's 0.09. Right, let's now talk about the binomial distribution. And there is a relationship between binomial and Bernoulli trial. First, Bernoulli trial are independent. So if I flip the coin and I got head, if I flip the coin second time, it could be head, it could be tail. It's not affected by the first outcome. Each trial has the same success probability. So the probability of head is 50%, next trial 50% is the same. Now, if I assign x as the number of success in n trial, then now x is a binomial distribution with two parameters, n, the number of trial, and p, the probability of success. And we say x is a random variable with binomial distribution. So basically binomial is carrying out the Bernoulli trial n time, and your variable x is the number of success. Let's look at this example. A fair coin is tossed 3 times. Let x be the number of heads that appear. What's the distribution of x? So basically they want to know what are the possible value for x, which is in this case the number of heads that appear in 3 toss of a coin, and the probability of x. Well, there is a probability that x0 mean no head appear in the 3 time we toss a coin, or maybe 1 time the head appear, or 2 time the head appear, or maybe the 3 toss came head. So we need to find what's the probability x equals 0, x equals 1, x equals 2, x equals 3. For now, it's easy to list all possibility. So the possibility is head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. So these are all possibility. Basically it is 2, since the outcome, only 2 possible outcome, head or tail, and the number of trials is 3. So that is 8, and that's the number of possible outcomes. So now let's say x represent the number of head. So for 3 heads, we have this is the only possibility. So that is 1/8. 0 head is this possibility. There is only one possibility where no head, and 1 out of 8. So that is the probability 1 out of 8. Now 1 head, I have these possibilities for 1 head. This is one possibility. This is another possibility. So there are 2 possibilities. So then it will be 2/8. Now let's see two heads. Two heads, I have this possibility, 1, these 2, these 3, so that is 3 over 8. Actually, we are missing this one. One head, there are actually 3 of them. So that is one head. There are 3 of them. So one head, this should be 3 over 8. So the total here should be 1. And that's 1. And that is the distribution of x. Another use of binomial distribution is you have a population, and this population contains items either working or not working, or items of two types, male, female. And we are taking a sample such that the size of the sample here, n, equal or less than 5% of the population. Why is this important? Because then every time I select an item from here to here, I am guaranteed that each trial is a Bernoulli, either working item or not working item, and independent. That means just because this came a working item, that doesn't mean the second one will be not working or working. Now, if my random variable x is equal the number of working item, now x is a binomial distribution. To find the mean, the variance of a random variable with binomial distribution, it's easy first to find the link between binomial and Bernoulli, and then it's gonna be easy to find the mean and the variance of a binomial random variable. So we can think of a binomial as a sum of Bernoulli. So if I have a population here, I am picking up items, then I can define x as a random variable that consists of the random variable y1, the first item I pick. It could be success or failure, plus another random variable with Bernoulli distribution. Again, it could be success or failure. And I can keep going to n selection or n trial. Now x is the number of success. So y1 could be 1 or 0, success or failure. y2 could be 1 or 0, success or failure. So if I sum them up, it will give me the value of x, which is a random variable with a binomial distribution. So now if I want to find the mean of x, mu x, it's the mean of y1 plus the mean of y2 plus the mean of yn. And since y1 is a random variable with Bernoulli distribution, the mean is p, which is the probability of success, and we already found that. So that would be p plus, again, this is a Bernoulli distribution with mean p plus all the way here p. So I have n of p, so that is np, and that is the mean of the random variable x that has a binomial distribution. So if I am picking 100 items from a population with probability 0.1 failure, then the mean, the average in the 100 I pick will be 100 times 0.1 is 10. So the average of failure will be 10 items out of the 100, and that's the mean. Now let's look at the variance. So the variance of x squared, it's the variance, let's look here, of y1 plus the variance of y2. So I can add the variance because each random variable here is independent, plus all the way to the variance of yn squared. So the variance of the random variable y1, which is a Bernoulli, we already found it to be p times 1 minus p, plus the variance of this one is p1 minus p, plus all the way to the nth Bernoulli random variable, so that's p1 minus p. So now I have n of these items, so then it would be np 1 minus p. And this is the variance of the random variable x that has a binomial distribution, which is this one. So we found the mean and the variance of the random variable x. Now I want to find the probability mass function. That means the probability px, which is the probability that the random variable x will have this value. And here x could be 0, 1, 2, 3, 4, all the way to the n trial. So how do we find it? We can think of it this way. If you have a population that has item success or failure, and you draw a sample of size n, and you have these items x1, x2, all the way to xn. Now if I ask you, these xn items here, if x is the number of success, well, there is a possibility 0, all items are defective. There is a probability there is 1 working and n minus 1 defective, and so forth until n working and 0 defect. So now if I ask you, how many ways can you arrange these n to be x working and n minus x defective, not work? And order doesn't matter. That means if I am picking 3 items, it doesn't matter if I have success, failure, failure, or failure, success, failure. All I care is how many success in these n items. So that is arrangement of how many ways you can arrange this n item with that many success x. So this is a combination. So that means it will be n choosing out of it x possibility, which is n factorial divided by x factorial n minus x factorial. So that's how many ways you can arrange n items with x success and n minus x failure. So now if I want to find the probability mass function, it will be the probability of success and how many success there are x item times the probability of failure. And the probability of failure is 1 minus b. How many failure there are? There are n minus x. And how many combination you will have x success and n minus x failure? This is how many combination. So that will be n factorial over x factorial n minus x factorial. And this is the probability mass function of a binomial random variable. A lot contain several thousand components, 10% of which are defective. So p equal 0.1. Let x represent the number of defective. What is the distribution of x? So we pulled 7 components. So that is here a sample n equals 7. So if I want to find the distribution, it will be this way. X, p of x, 0 defect, 1 defect, 2 defect, 3 defect, all the way to 7 defect. Now, if I want to find the probability, for example, x equal 2, that will be n factorial, which is 7 factorial, divided by x factorial, which is 2 factorial, n minus x, 7 minus 2, that is 5 factorial, times the probability of defect, 0.1. How many defect I have? 2. Times the probability of not defect, 1 minus 0.1, time how many not defect? 7 minus 2 is 5. And if you calculate this, you should get here 21 times 0.01 times 0.9 to the power of 5. And this should give you 0.124. So here it will be 0.124. And you can do the same thing for x equals 0, x equals 1, x equals 7. We can do this example, but here n is 10 bits. Probability of bit error is 10%. And what is the probability that 3 bits will be corrupted out of the 10 transmitted bit? In this case, it will be probability x equal 3. It will be 10 factorial, 3 factorial, 10 minus 3 is 7 factorial, times the probability of corruption of error, there are 3, times success transmission, 0.9, and there are 7 bits arrived, not corrupted. And you can calculate this probability. In this example, a large industrial firm allows a discount on any invoice that is paid within 30 days. Of all invoices, 10% receive the discount. In a company audit, 12 invoices are sampled at random. So we have here a population of all invoices 10% receive discount. So in a company audit, 12 invoices are sampled at random. So here n equal 12. What is the probability that fewer than 4 of the 12 sampled invoices receive the discount? So they want to know what is the probability that x less than 4. This is the probability x equals 0 plus probability x equal 1 plus probability x equal 2 plus probability x equal 3. And if I calculate probability x equals 0, that will be n factorial divided by 0 factorial. 12 minus 0, that's 12 factorial. Probability of discount 0.1, 0 received, probability of no discount 0.9, and 12 voices received no discount. Now probability out of the 12 only one invoice received discount. It will be 12 factorial over 1 factorial 11 0.1 to the power of 1, because there is only one received discount and 11 didn't receive, so that time the probability 11. And probability x equal 2 will be 12 factorial over 2 factorial 10 factorial 0.1. There are two of them. No discount, there are 10. And last, probability x equal 3 equal 12 factorial over 3 factorial times 9 factorial. There are 3 of them receive discount times 0.99. Now if you calculate all these probability, you should get here 0.282, here you should get 0.376, here you should get 0.23, here you should get 0.085. So probability x less than 4 equal 0.282 plus 0.376. All right, so it's just the sum of all these 4 probabilities. Now in reality, when you have this population, you don't know the probability of success in the population. Or if an instrument manufactures transistors or memory, and you want to test what is the probability of success, that means working transistors. How do you estimate that probability? Well, we take a large sample usually. So n could be 200, 1,000 transistors, and we test them. And we count the number of success, x. And then we estimate the probability of success will be x, the number of success in this sample, divided by n, the total number of transistors we tested. Now the question is this estimation of P biased or unbiased? And what is the uncertainty in our estimate? That's what we need to calculate. So let's start with the equation we used to estimate the probability of success. It's the number of success divided by n, the number of trial. Now, if I want to find mu of the random variable p, it will be 1 over n, that's a constant, time mu x, and that is 1 over n. X here is a binomial distribution. So the mean of x is just, we found it in the previous slide, np. So you cancel n with n and you get p. So the bias is the average of the estimate minus the true value. So if I plug for mu p here, p, then minus p is 0. So the bias in this estimate is 0, so p hat, the estimated p, is unbiased. Now the question is uncertainty. How certain are we in our estimate? And uncertainty, basically you calculate the variance. So that means if we start with this equation that we use to estimate p, then the variance of p hat equal 1 over n is a constant, so that's 1 over n square times the variance of the random variable x, and that will be 1 over n square. And we already found the variance of a binomial x is just np times 1 minus p. So this is p times 1 minus p over n. So I have n squared in the denominator, I have 1n here, so they will cancel. And the standard deviation, which is the uncertainty of the estimate of the probability, will be the square root of the variance. So that will be P1 minus P over N. That's the uncertainty. So we may find P hat to be 0.4. Then the uncertainty will be like plus minus something. And that's what we mean by the uncertainty. For example, if I told you here, testing a transistor, you took 100 transistor, so that is N, and you found 7 of them defected. So the probability of defect will be 7 over 100, that's equal 0.07. So that's your estimate of P in this population. Then if I calculate the uncertainty, I can plug for P here. I don't have the actual value, so I will plug the estimated here and calculate the standard deviation. So then it will be standard deviation of P is 0.07. 1 minus 0.07 is 0.93 divided by N. I have 100 transistors that I tested. And if I do this one, then I should get 0.0255. So then my estimate of P will be 0.07 plus minus 0.0255. That means the probability of failure could range from 9.55% and as low as 5%. Let's do this example. The safety commissioner in a large city wants to estimate the proportion of buildings in the city that are in violation of fire code. So let's assume here we have the city. A random sample of 40 buildings, so that is N equal 40, is chosen for inspection, and 4 of them are found to have fire code violation. So here X, we found it to be 4. Estimate the proportion of building in the city that have fire code violation. So then our estimate of probability that violation, we found 4 out of 40, so that is 0.1. So 10% of the houses in the city have fire code violations. Now we need to find the uncertainty in the estimate. Well, the uncertainty in the estimate, we found it to be the square root of P times 1 minus P divided by N. So that is square root of 0.1 times 0.9 divided by 40. So this is 0.0474. Now they said here, how many additional buildings must be inspected? So the uncertainty in the sample proportion of building in violation will be only 0.02. So we are not satisfied with this big uncertainty. We want it to be 0.02. So what can we do? If we look at the definition here, the only thing we can change to make the uncertainty very small is the number of trial, or in this case, the number of houses we need to test, which makes sense. The larger the number of houses you test, your estimation will be better and the uncertainty will be less. So let's see how we figure out how many houses do I have to test so my uncertainty will go to 0.02. So we are gonna solve this problem now. The uncertainty is 0.02, that's what we want. And we're gonna be using P here and P here, the 0.1 estimate. And here we will have N. We have to solve for N. That will give us this uncertainty. Now, in real application, if I increase N to 100, that P here will also change. But let's assume that we are increasing N, that won't change much. So we are using this value here, 0.1. And if you solve this, so we can square both sides, and I will have here 0.02 square equal 0.1 times 0.9 divided by N. And we can solve for N. This will be 0.09 divided by 0.02 square. And this will give us 225 house. We need to inspect to reduce the uncertainty to 0.02. Okay, I'll stop here and we will continue next video in section 4.3, which is the Poisson distribution.